Hi, my name is Rod Strange. I work for a company called Teraspeed Consulting. It is a division of Samtec. We have a Samtec booth outside. We are SIPI consultants. And we do DDR3 and DDR4 designs on a normal basis, so thought we'd do a presentation on it. We are not part of Mentor. This is a consulting group, and we use the Mentor tools. So ask any questions you want. I am not a tool person. We use their tools, but that doesn't mean I can answer all your questions on the tools. That's what the Mentor people are here for. But I have this presentation and another presentation after that on some issues with some high-speed SerDeses. So how many people in here have done DDR before? I would think all of you. Okay, how many have done DDR4? Okay, DDR3. You're not raising, so have you done DDR at all? But 1 and 2. Okay. And have you all used this tool to do it? The Mentor tools? Pretty well?
Have used their simulation verification.
Okay. Yeah, the simulation tools, they do have a nice DDR wizard in there, which is kind of nice. So ask questions as we go. If they're too detailed, we can talk offline and see what kind of things we weren't looking at. What we want to do is, I want to look at the difference between DDR3 and DDR4, because there are some differences. I want to look at some stack-up considerations. So the big thing is the company we were doing this for wanted us to do, of course, all manufacturing variations, best case, worst case, board stack up, impedance changes, everything, because this was going to go into a heavy-duty situation. So we wanted to make sure of that, and we had to do it with crosstalk and simultaneous switching outputs also. So from the SI perspective, what's the difference? I'm not going to go into big functionality. You guys probably know all this. But from my perspective, since I've done more threes, obviously easy stuff is the voltage, and of course that is for power. Second is the VREF inputs. They did away with some VREF inputs, and now for the DQs, the VREF is made inside. So that makes it a little bit easier on routing, A, on routing the VREFs, and B, for any noise or crosstalk on the VREFs when we have a problem, so it has it inside, and that's part of the training algorithm. I'll go over that later. They're faster. And DDL enabled, it does have a minimum and maximum range. They did change one of the output drivers. Remember, you can choose the output impedance, anything. They just added one. And on just the DQ bus, it went from an SSTL, remember, subterranean internal logic, to POD, which means pseudo open drain, which is, they kind of made it up. It does have an open drain. I'll talk about that too. They did that for power, because as you know, we go up in speed, the power is going to go up too, CVF. RTT values, they added some for better, that means lower power. They, of course, still has ODT on determination. They did change some of it. They added a little bit more functionality. They have the calibration, which is good. They have data bus inversion, DBI. We never used it. It's supposed that you'll be able to invert the data bus depending on the pattern, so you'll have less noise. Switch too many high or low. Never implemented it, so I don't know how well it works. Look, they've got parity in CRC back again after all these years of dumping it, which is kind of nice. A lot of our customers do like that. So it's air data connection on the command address bus, and the CRC is on the data. So you do have them both covered. Do you use any of those things? Is CRC important? It is for the military, and that was about it. They're kind of used to not having it because it hasn't been around for so long. Here's a list of the plus minuses, how many they added, how many they took away. Notice they added and took away, so the only difference is, I think, 2 pins. So, and you can see which ones they added and which ones they took away. For most of us, we probably won't even use it. test enable, parity, alert if you get an error on your CRC, some of those things. I haven't seen a lot of controllers even play with this yet. I think that will change as the controllers get a little more sophisticated and get used to doing it. But they took away a lot of the pins, especially the bank addresses. So the difference between the two was not a big change. None of the packages changed, nothing of that. They just added some more. Now, this is what they call the pseudo open drain. To me, this is the way CMOS used to be. Remember the original CMOS pulled down really well and the pull-up was really small, like the original TTL? Remember, pull-down was typically 8 times as much as pull-up? Well, they're doing it here on purpose because normally the P and N channels, we have equal pull-up, pull-down. On this one, they make this really weak in what makes your pull-up? Your terminator resistor, which means you take the power away from the inside of the RAM and put it on outside. Does it save power? Well, not particularly, but it does move it because you know some of the DDR3 and 4 parts get pretty hot. So they pulled that out. They got that from the GDDR5 spec, if I remember correctly, and tried it. It works well, you just have to have that outside resistor, okay? And I think I went into that a little bit more. Don't forget this, and I've already seen this happen. On the data bus, it's changed compared to the rest of the buses. You're used to this for all the signals before. Remember, it's VDDQ divided by 2. In other words, it's center terminated, right? That's not the way it is on the data bus. Don't forget that. Now on the data bus, since they need this current pull-up, now what they do is they put it on the outside, and that is your pull-up terminator. And don't forget, where does it go? It goes to VDDQ. It does not go to half, because half won't give you the pull-up. When you do the middle one, you know, half up, half down, with your Thevenin of V terminator, it's not a problem because it's right in the middle. But if you're doing a pull, there's no pull-up on the inside of the part, you have to pull up on the outside, that is going to change your termination, where it is, and that will change your switching values inside the part because of the pull-up there. So don't forget to change this part. That's pretty easy if you know what you need to do. And then from, this is just, they changed this a little bit. They do now the calibration, they call it V-center of the DQ. So they move what the center is. In other words, where do you put the switch point? You got an eye, do you put it up here, down here? And it does that dynamically. How much did they do that on DDR3? I forget. I don't remember this part. And this is done inside. So they move this VREF DQ inside internal so that they get the best switching characteristics. Okay? You do not have to do that yourself. So now they look at an RX mask and data eye. So it is changed from the standard setup and hold time, and now they look at an eye instead, and then move the center around. So each DRAM is individually calibrated inside the part, each memory part itself. And it looks like this. Here's your data eye and here's your mask. What they are, they have 2 different sets of VDDQ. One is the higher step, which goes to 90% and goes down to 60, and then 175 to 45. And it will choose which one it needs to get the best timing and noise margin, which is great for us. You don't have to worry about that, but you need to know that it happens because on your tool, where does this go? So you have to do a little bit of correlating on that.
Is that still done only at startup, or is it done continually?
I think you can give a command now that will do that for you. Yeah.
Yeah, they do have run for that.
Well, yeah, it's startup, everything looks wonderful. Come on, everything's cold. Look how fast we are. And then it heats up and everything's gone.
If you in the past, I've had to work around it with the temperature chamber, right? To heat the board up first and then restart it. It's been the only viable solution.
Is that what you do?
That's what I did on my DDR designs when I was before I came to Minter. I had to put it in a hot box first, get it out of room temperature, and then restart it, make sure it's still.
Got to get those junctions hot. Okay, we're going to look at some of the stack up. Now, this is not a typical stack up. This was just a board we used, but I wanted to show you what we think is important on a stack up. Obviously, for just DDR, we don't need 22 layers, but there was a lot of other things on this board. So, you know, where do you put your planes? Minimize the inductive path on the planes because some of your high current items, you would like those planes to be close to the part. Come on, if you're going to feed them with vias, vias have inductance, which does change your power characteristics. And then you have to understand what needs to be next to a ground plane, what needs to be next to a power plane. And I think most of us know is you don't mix those. When you have a reference, notice on address, command, and control, it's layer 3 and 20. You can look at this. But the point is it's ground and power reference. And then when you have clock and address command, that is layer 5 and 18. It's still power and ground, which means you can go between these references. You can go from one layer to another. And then for your DQs and DQSs, what are they referenced to? Ground and ground. Now, what's that mean to us? That means if you've got a signal and it's referenced to ground and you change layers, do you want to go to a layer that's referenced to something else other than ground? Well, I hope not. Changing reference layers will destroy your signal. So you need to hold to what the spec is, and unfortunately the spec can change depending on the controller. What layers do you use for references? For an example, a DIMM chip tells you what the references have to be for the data control. And if you do not follow those and you're using DIMMs, you'll change references when you go to the DIMMs, and there's a big chance your parts won't work. Okay? And if you're not using DIMMs, then what references do you use? What references do you use for the DQs and the addresses? Easy answer is, it should be in the controller specification. Because don't you have a printed circuit board in your controller? Of course, your substrate. That sets the references because they set the traces next to a reference. That's your reference return current plane, and you need to keep those consistent. Just don't route them out of your controller to any layer you want and then up to the RAM. It might not work because then you get split planes and reference changes, and that's not a good thing. Matter of fact, this is from a 3D simulator. Here are 7 lines. I use the middle one as a victim and fired the other 7, and it went over a split or it changed layers. They look the same. Changed layers so that the references were not consistent. Reference return current consistency, we call it. Here's what it's supposed to be. Here's what it turns out when you cross over and change references. I don't think you want that. So if they're a reference to ground, you keep them on ground. If they're a reference to ground and power, you keep them on that. If they're a reference just to power, you keep them referenced to power and you don't change it. If you do, instead of the nice blue line, you'll get these. And that's an incredible amount of noise. So a lot of people don't think about that when they lay the board out, especially if you DEs, you design engineers, don't give them rules. How do they know what layer? So you need to give them rules that what layer to use? No, I don't care what layer to use. I care what reference you're doing your signals to. Is it a ground reference signal? Is it a power reference? That's what you give the engineers, and you put that in your stack up saying, okay, data has to be on this layer. Do I care if it's on that layer? No, I care because that's where the reference is that you need to be on that layer. Most of us, you guys already do that, yeah? Okay. I still see some guys that haven't done DDR before and they switch them all up and it never works. Need to keep track of that. And then we do all the variations of all these, and then you have to think, of course, your length matching and your crosstalk effects. Because we would love to route all this stuff at minimum spacing. You know it doesn't work that way. Operating frequencies, you all know this. You're in your clock and data here, you double it, it doubles this. And then your 1T timing or 2T timing. On your last design, did you get 1T? How many rows did you have? Memory. That's pretty good for 1T timing.
Yeah, I've never done 2D.
Well, on motherboards, you know, you got a DIMM, typically 4 or 3 DIMMs. You plug in one DIMM and you get the 1T timing, so it's really fast. You know, you get your motherboard specs or your specs and it says, look at our speed of our memory. Well, you add 1 or 2 more in there and the speed changes because the more memory you add is the more loads. What happens to the signals? They get slower. So we did 1T timing, but it wasn't very deep. Keep that in mind. As you add parts, that means that you're going to add loads. And adding loads affects your timing.
I think I told you wrong. I think it'd still be 1 row. That's not enough for chips, right?
Now, on your chips, like we had 9 in a row. If you wanted to add another row, now we haven't. That's what we do. And that's why, like on the newer parts, like your motherboards, they'll have 2 and 3 different memory channels. Well, you add different memory channels because it loads them less, and you could do simultaneous accesses. If you just keep putting memory in another one, your system's going to get so slow. So even a lot of the FPGAs and the controllers will do at least 1 or 2 different banks. That makes your system faster and a lot easier to design too. So that you can run things at 1T instead of 2T, and 2T does make a big difference. Well, you are all Mentor users, yeah? So you know what this is a picture of. You can either extract this, of course, this was extracted, or you can make this yourself and put individual values in. Because, as you can see, there's a driver, a transmission line, a via, a transmission line which has impedance and length and da-da-da. A via to go up to the loads, 9 loads away across. And here's your clock. As you can tell, it's differential pair. So you can do this by hand, which I've done, or you can extract this from a routed board. And from that, you can do your simulations, moving these around, making variations, so that you can do your corners. Now let's look at one. Let's look at address, command, and control. There are 3 different signals there. Which one is which? If you didn't know that I color-coded these, 1st, 5th, and 9th, can I look at this and tell what those are? Some of you guys are signal integrity guys. If you have 9 chips in a row, which one is always the worst SI? First. Why is the first one always the worst? Because most guys that are getting into SI going, it's the first, it's going to be the best. It's all those stinking reflections. So it's the worst one is the first, and you can see, look at all the noise on this, because as you go up here and hit the load, what's a load look like? Capacitor, which is going to reflect. Remember, what's a small capacitor look like on an edge? A little short, reflects it back. You go to the next one, reflects it back. You go to the next one. So all those reflections from all of these loads go back to the first one. And then, of course, over here it's terminated. So usually the best one is where? Right there. You can see the middle one, and then the first one is the worst one. Now, all of these go away if you take the capacitors off the models. It's an easy way to test it. And, you know, with the IBIS models, that's easy to do. I always have a collection of IBIS models that say NC, no caps. And then no inductance. I have models that are just perfect. They're just there. They're an oscilloscope. And then I build upon this and see what it happens. Because you take the capacitance off, these all look really nice. Questions on what I'm saying here? Because you got to simulate all this stuff. And then we have to look at matching guidelines. Well, since some of you guys have done 3, what kind of rules did you use for matching, length matching on your traces? Or you didn't care, you just said, hey, just route it, it's fine. It'll work, don't worry. You know, we got to get this thing done today, let's do it.
PCB manager just makes them all of a sudden, because it simplifies things.
It's a little bit more work. And in some places, depending on how the routing density, throwing a little serpentining in there can be a real pain in the butt. Then if you get things too close, what happens? Crosstalk goes up.
Address and column match group, data lane matching as long as the control is okay with that. So that they're different, DQ0 through 7, you get some match group.
Now, I hope you heard what he said. Match them within lanes. I had one design, he matched every single lane to every single, you know how much work that was? Match 8, and don't worry about the other stuff. That went away a long time ago. Your address lines, yeah, you got to match those a bit. We usually match it better than 50. That's too big a number for me. And I talk to the layout guys, and they're going, 50? That's going to the next state. Come on, guys, we can do that better than that. So most of the guys I work with, they match between 5 and 10. And I said, with the grid routing, what's the problem with that? You understand what I'm saying? You still got to match these things. Okay? And it depends on your topology. You don't have to have exactly one topology. You can change them and do T's and things like that. Most people don't, but it does work. And then the next one is, how close can your signals be routed next to each other? We would all love these to be minimum spacing. Love everything to be minimum spacing. In almost all cases on DDR3 and 4, you cannot route minimum spacing because the crosstalk is too high. Even on your motherboards, if you take your motherboards and flip it over, that's usually where a lot of the DDR is. They're not routed to minimum spacing. Look at the DQs and look at all those. They're not minimum. Why can't we make them minimum? Crosstalk just goes up. Especially, remember, on your outside layers, remember those are microstrip, the crosstalk has what? Forward crosstalk, which grows with length, linear length. You double the length, you double the crosstalk. On the inside layers, there's no forward crosstalk. It's only reverse crosstalk, and once the crosstalk goes up to what we call the critical or saturated value, it never gets any larger, which is nice. You make it this long, you make it this long, they have the same crosstalk. So, but if you have a limited number of layers, you'd like to use the outside layers. So if it's a bit longer, the traces on the outside need more space than the traces on the inside. If they're shorter, they can be the same. How do you know this? This you do have to simulate. Because what does crosstalk noise do? Changes your timing. Crosstalk moves energy from one trace to another trace, which changes your timing, and then you won't make your timing budget. So, yes, you have a maximum crosstalk allowed in your system, but what else do you have? You have a maximum timing budget, and they're both related to the crosstalk itself. Now, you read a lot of these books and things that give you guidelines. The guidelines are very conservative. In other words, they want one trace to another trace, 0.1 to 0.2 miles, okay? And you're going, oh, wait a minute, how am I supposed to do this board? Well, if you route it that way, it will work. But it's not going to help you guys make a nice small board. So you do need to try some of this and see if you can be more aggressive. Because remember, these depend on length if you're routing on the microstrip, the outside layers. Then how can they give you a spacing? They cannot. So you need to look at what kind of rules. These are the rules we got out of the controller. Did we route them all that way? No. But you look at the eye diagram, check all your timing, and test it. Now, don't route your entire bus. Okay, well, now we'll simulate it. Don't do that. What we typically do is called the 1-6 rule. We route 7 lines, one of them is a victim in the middle, 3 up, 3 down, right? Simulate it. See if it makes crosstalk. If it doesn't, what do? You start moving it apart, simulate it. If it doesn't work, you keep moving them apart, and then you're going, oh, here we go. Okay? Because 3 up and 3 down, if you don't have traces on the bottom underneath it, typically will give you about 96 to 98% of all the crosstalk. That's good enough. So, because you're going, well, I can route the entire data bus or the address bus and then test it. Well, then if it doesn't work, you have to reroute it again. That's a waste of time. So just do some experimental cases. Now, I always start routing a minimal. No, that doesn't work, but that's what I want. Then I go, okay, let's move them 2 mils. Try them again, try them. Oh, here we go. That's the rule I use. And then you can give that rule to your layout people, and you know it's going to work. Now, when the board's routed, when you route the DDR, do I simulate it all again? Oh, yeah. I don't trust any of that stuff. And he could have made a mistake. You could have made a mistake. Always do a post route. But don't do a post route as your first simulation. That's a waste of time. I can see from your head shaking you do that anyway. Don't just route it and say, well, does this work? And your layout guy will get real upset if you have him route it 10 times. He will take you out in the parking lot. So these are guidelines. Now, some of them are really great guidelines. I use more than just the guidelines. I'm going, this must be more important. So they give you some information more than just the guideline. Okay? Yeah, I had to put a special note. Don't route the whole bus. And a lot of you have looked at the specs on DDR. That's just a part of them. You know that goes on for pages, but come on, it's a small Britannica. And no one's going to read all that because you won't remember it after you've read the first 10 pages anyway. So there are a lot of rules, matching, guidelines, timing, everything. Look at all the rules. Too much. So that's why a wizard really helps, because there's an incredible amount of data here. Okay? And you need to be careful on one thing. A lot of the controllers do not meet the JEDEC spec. There's a couple of lines they couldn't make, but they tell you how to fix it. In other words, maybe it's a little shorter length or a little bit of timing. Make sure you look at those in the controller spec. Now, the DDRs themselves, the memory itself, they're good at that. I mean, that's all they do is that spec. But some of the controllers have had difficulty. They'll figure all that out later, but some of the first ones had a little difficulty. Make sure you read those. And the second part is they had difficulty on matching all their lines. We saw some controllers that said on A3 you would need to add 8 mils because they couldn't get it in the chip. Okay? So don't forget those things. And sometimes, unfortunately, they're stuck in the back. You know, look at reference 12. It's worth looking at.
So on the timing models for DDR simulation, do you typically use the built-in hyperlinks timing model for the DRAM?
Yeah.
Because I wouldn't imagine you would need to build one for...
Yeah, it's just the JEDEC spec. Now, what you do is they have the standard controller one. You go through and change what you need to change. Because since you've used it, you know there's a lot of numbers in there. So change that part. Now, I can't tell you which ones they are. That depends on what the manufacturer is and see what they have. And that's not uncommon. For the first year or two they make them, they push it pretty hard, so some of them they can't make the specs on. So, this is your sheet that says pass-fail. Notice these are passes. And you can click on any one of those, and it will give you the simulation result. Now, I hope that every one of you would click on every one of those and look at every waveform. Or do you guys say, well, look, it says pass on everything, we're done, ta-da. No, click on every one of them and go down it. You don't have to do anything else. You click here, it brings up that simulation. Go through every single one. Doesn't take that long. You put the headphones on, put your Pink Floyd music on, typically Dark Side of the Moon, because it's brainless activity. And you go through every single one because you might find a bad one that the tool didn't pick up. You want to look at the simulations, not that many of them, and make sure you've got everything right. Okay? So as a company, we wanted to know how good the simulations were for the hyperlinks. Come on, there's lots of simulators out there in the world. Most of them correlate really well. This tool correlated quite well. And that made us happy because it's a lot easier to use. So these are two different simulations from two different tools. Actually, there are four of them, but you can barely see the yellow underneath. So we used a 2.5D field solver, one of the more popular ones out there, and we used hyperlinks so that we can compare them. And you can see that correlation is quite good. This is the ground referenced. Remember, we have different references on different signals. Understand what I'm doing here? Two different tools, four different traces, and they're really good. Then we did this same thing with the chips, remember? First, fifth, ninth. Other than a little timing skew, they look great. Why would we want to do this? Well, some of the 2.5D tools are touted quite well, but they're hard to use. They're really hard to use, and they take a long time, a lot of compute power. So we wanted to make sure that we can use this because it was so much faster and easier with the wizard that, well, come on, what's my favorite tool? The easiest one to use. Come on, I don't want to sit on my desk and beat on it all day. I want the easiest tool that will give me good results. So we did this with hyperlinks, and we also did it with a 2.5D. To do the same simulation took 1,021 ports. And if you've ever used any of these tools, you know that takes time. It's a pain. So we wanted to do that, and then we did it for the power referenced. And we felt pretty good about it. First, fifth, ninth. Any questions what I'm saying here? We wanted to do a validity report to see, because the speeds are getting high enough to see if the simulations correlated well, which they did. So that gave us a better feeling on, you know, our customers always ask, well, what tool did you use? And, you know, what was your methodology? Da-da-da-da-da. Well, then we could tell them it was fine. So now that we got the tool situation, that, hey, they both work, we did the worst case analysis. We did the crosstalk analysis, which please guys do. Unless you want to, you know, have them all spread out, and then it's going to cost you layers. So we went through all this, which, since you guys have done DDR3, did not take 1 or 2 days. We can still use 1 or 2, but don't put days in front of it. Use a different unit. And typically, I wouldn't put weeks in front of it either, okay? We know how long this takes. So we do DDR a lot. So we wanted to kind of make a presentation to show that we trust the tool's easier to use with the wizard, and it worked out well for us. Systems in production works fine. Now, I'll give due its place. Ruta Bakle is a signal integrity engineer at Teraspeed. She did this paper, I did not. But I'm the one that does the traveling. And Samtech, our owner, makes a lot of parts for high-speed signal integrity. A lot of good parts. Go outside and check out. We make our own cables, high-speed cables, really high-speed cables. Own high-speed connectors, everything. Our own substrates. And this was the user-to-user show, April, in the Bay Area.